Hello everybody! In this video we're going to talk about the polarization of light. Now there is a PowerPoint presentation. You can find it on our course page right here. Now in this presentation we do talk about polarization, but I also mentioned just a little bit about scattering and absorption. You're not responsible for the scattering and absorption. In fact, you're not responsible for everything we say about polarization. I'll let you know what you are responsible for. And when I say responsible for, I mean possible test questions. Okay, so I'm going to talk about all these things, but if you want to end the video, stop watching the video after I say, okay, from here on out is just bonus material, I completely understand. Also, some of the things we're going to talk about are much easier to see in person with actual demonstrations. So if I see you in person, we'll do some demonstrations and I'll let you get your hands on linear polarizers, for instance, and play around with them. Okay, but in any case, let's go ahead and discuss polarization. Oops, I want to start my slideshow. There we go. Okay, so when we talk about the polarization of light, what we really are referring to is what is the so-called electric field oscillation axis doing as the light's propagating? Now, I'm focusing on the electric field. Just realize that the magnetic field, it's always oscillating perpendicular to the electric field. So when we're talking about linearly polarized light and we're talking about the electric field, right, is linearly polarized, so is the magnetic field. Okay, it's just along for the ride. Okay, all right, so what is this oscillation axis doing as the light's propagating? Okay, so depending on that, we have different polarization types. So unpolarized light just means as the electromagnetic wave is traveling, this oscillation axis of the electric field is just changing randomly. Okay, so the axis is not fixed, nor is the axis rotating in a definite pattern. So the axis is just changing its direction randomly. We call that unpolarized light. And a lot of light is unpolarized. Light directly from the fluorescent lights in our classroom, for instance, is unpolarized. So is sunlight. If you just look at the sunlight coming through the air, it's going to be, the majority of that will be unpolarized light. Now, if the axis is fixed, so as the electromagnetic wave is propagating, going, let's say, up and down, right? That up and down axis never changes its orientation. We call that linearly polarized. Sometimes we hear that called plane polarized light, okay? If the axis is rotating, right, with a definite pattern, and the amplitude of the electric field is constant, so the amplitude's not changing, then that's called circularly polarized light. Okay, now you can have this rotation of the oscillation axis, but the light does not have an equal amplitude depending on the direction. Okay, so then that's called elliptically polarized light. In fact, if the amplitude changes in such a way that if you look at the tip of the arrow, the amplitude arrow, as the axis is rotating, that tip will actually trace out an ellipse. Okay, so linearly polarized light can be produced naturally. We can also produce it, quote, artificially, so we can do something to light to make it linearly polarized if it's unpolarized. And that's what we're going to talk a lot about next, is getting linearly polarized light from unpolarized light. And then some characteristics of linearly polarized light. Circularly and elliptically polarized light can be produced naturally, and also we can produce it with different optical elements and engineering how light behaves in materials. Okay, so here is that picture that we've seen before when we first introduced the electromagnetic wave, and that is linearly polarized light. That's what a, quote, picture of it would look like. You can see that the purple electric field wave, it's always going up and down along the y-axis, and that axis always has the same orientation. Realize that the magnetic field is oscillating perpendicular to that, in this case, in this picture, the z direction, and the light is propagating in the third perpendicular direction, which would be the x direction in this picture. Okay? So that's an example of linearly polarized light. There are different ways to represent the polarization state of the light in construction diagrams, so I thought I'd show you that because we're going to use these symbols and diagrams in just a little bit. So if you want to represent unpolarized light, you could do something like that. So imagine the light is actually coming out of the screen at you. By drawing the arrows like that, you're saying that at this moment in the plane of the screen, the electric field could have any arbitrary orientation. Okay, so that means unpolarized light. If you want to represent linearly polarized light using the same type of symbol or picture, it would look like that, for instance. So again, you can imagine the light's coming out of the screen, and you've only shown two possible directions for the electric field in the plane of the screen. Now, if I rotate that axis so that I have those two arrows and on a diagonal, that still will be linearly polarized light. Okay, it's just nothing special about the vertical. The fact that there's only one axis for the electric field oscillation makes it linearly polarized. Okay, so let's talk about how we could get linearly polarized light from unpolarized light. And there are some applications where you'd like to do that. If you know the light is polarized in a certain direction, then you may be able to control the amount of light that gets through your system, or you might want to study some material properties, optical properties, I should say, of a material, and you might get different optical responses depending on the direction of the electric field oscillation axis, the polarization axis. Okay, so standard way to do this is with what we usually call a linear polarizer or a dichroic polarizer, and then the trade name for this would be a Polaroid, because Polaroid I used to have a patent on a process for making these polarizers. And again, if I see you in class, I'll give you these. What this is a thin sheet of material. It's usually sandwiched between two pieces of glass or plastic to protect it. Not necessarily, but the material is such that there will be a so-called transmission axis or polarization axis for this sheet. In this picture, the polarization or transmission axis is along this direction, right? Not quite vertical in the picture, okay? So what happens is if you send in unpolarized light, here comes the light, and it's going to go through the polarizer. Notice that we have that unpolarized symbol here, right? The electric field axis could be in any direction. What happens is that any light that gets through will have its electric field axis parallel to the polarization or transmission axis of the polarizer, okay? Now, it does this through absorption of light. So you are going to lose light intensity. Ideal polarizer, if this is truly unpolarized light, you'll get 50% of the light intensity coming through. Again, that's an ideal. No polarizer is perfect. The absorption process is not 100% efficient. Okay, but in theory, if it's perfect polarizer, 50% of the light will get through, and that light will be linearly polarized. Now, the way it actually works is it worthwhile to tell you how this works? I think it's worthwhile. If you want to fast forward through here, you can. But maybe what I should do, let me end the show. And now I'm sure I messed up my recording. Is my recording still going? I think it's still going. Yes. Okay, so the way this works, let me just sketch something real quick, is in this material, this so-called dichroic material, you have these long molecular chains. So let's say this is your polarizer. Oh my gosh. And this is the polarization axis. Well, if you look in here, you'll see these long molecular chains like this. Oh my goodness. So these represent these molecular chains oriented horizontally. Now, as the light comes in, you have to look at it in terms of components of electric field. Electrons can move very easily horizontally in my picture because the electrons can move along these molecular chains, right? These outer shell electrons pretty easily. So any electric field, remember the fields are carrying the energy. Any electric field oscillation that's horizontal, the energy from that component will be easily absorbed because that horizontal electric field can easily drive the electrons and they can absorb that energy and move horizontally. The electrons can't move very efficiently vertically. So if there's an electric field that's vertical and is trying to drive the electrons through the electric force vertically, the electrons just can't do much. They can't absorb energy efficiently from that field. So what comes through here is light, which is primarily polarized vertically, right? Because the energy from these vertical field components can't be efficiently absorbed by the electrons. So that's how it actually works. It's pretty cool. Okay, so let me see if this is going to work. If I go back and get through, yeah, I think it's going to work. So, for instance, here's the transmission axis, right? So if I have, let's say, my electric field like that, at some moment my electric field is pointing like that, I can think of this field vector as having two components, one perpendicular to the transmission axis, one parallel. The energy from the perpendicular component is easily absorbed. That can drive the electrons efficiently. The parallel component, the electrons can't get the energy efficiently. They can't travel very well in that direction. So that component gets through. So it's really, mathematically, it's this dichroic polarizer is selectively allowing just that parallel component of the field through. So again, pretty neat. Okay, so here's a little quiz for you. What if that's my electric field direction at this particular time and the polarization or transmission axis of my polarizer is parallel to it? Question is, how much of the light gets through? Well, theoretically, all the light passes through. Okay, now again, the absorption process is not 100% efficient. Okay, so, and in this case, some of the light will get absorbed. Okay, right? It's not 100% selective. Okay, what if my electric field's vertical, but my transmission axis has been rotated a little bit? Well, then that component right there is not going to get through, but that component will, so I have less light passes through compared to the first case. And if my axis of the electric field is vertical and my polarization axis is rotated even more, then I think less of the light should get through because the component parallel to the transmission axis of that electric field is smaller. And then if we get to this case, where the electric field is perpendicular to the transmission axis of the polarizer, then theoretically, no light should get through. But again, a little bit's going to get through because the absorption process is not 100% efficient. Okay, so what you can do then is play around with two polarizers and reproduce what Malus observed a long time ago. I'm not sure how many hundreds of years ago or decades ago. This is called the law of Malus, and what you do is you produce linearly polarized light. That's what your first polarizer does. So you could take some sunlight, for instance, and put a linear polarizer here. So the light coming through here will be polarized parallel to this transmission axis of the first polarizer. Now suppose your so-called analyzer, the second polarizer, its transmission axis is at some angle theta with respect to the first polarization axis. Okay? Well, if you look at the component of E naught here that hits this second polarizer, the component that's parallel to its transmission axis is E naught cosine theta, where again theta is the angle between the two axes. The intensity of light is proportional to the field squared. So the intensity that gets through the second polarizer should be the intensity that hits the second polarizer times the cosine squared of theta. And you can observe this in practice. And this is called the law of Malus. So you should know the law of Malus. By the way, when Malus did this, he did not have polarizing films produced by the polarizing company. But there are natural dichroic polarizers. In fact, if you were a rock collector when you were younger, mica is a rock, and it loves to cleave in really thin sheets. So thin that you can get some light through them. You can see through them. And they are naturally dichroic. They have a polarization axis that selectively absorbs light. So you can do this with mica. Pretty cool. And again, if I see you in person, you'll see a quick visual demonstration of this. Notice that when the angle between the two axes is 90 degrees, there should be no light getting through, which is what we saw in the last slide. And the most light's going to get through when the two axes are parallel, so the angle theta is 0. Another thing you should know is how light can be linearly polarized when it reflects off of an interface. And just focus on this second picture, because there's a lot going on here. And if I try to discuss everything that's going on in this first picture, it's going to take too long. So just look at the second picture. It turns out that there is a special angle of incidence. It's called theta sub p, the polarization angle. An older name for this is the Brewster angle. So that when you look at the light that reflects off of this interface, all of it will be linearly polarized. And the way it will be polarized is indicated by these little dots. So these little dots are supposed to represent arrowheads. So look at this incident beam. It can have a component of light that is parallel, right? These orange arrows. Remember, the electric field has to be perpendicular to the direction of propagation. So these orange arrows are perpendicular to the blue incident ray. So that's one possible component for the electric field of the incoming wave. But another possible component would be the electric field axis going in and out of the viewing screen. And that's what these little black dots are representing. They're representing the points of arrows that are pointing directly at you. So the incoming light could have an electric field component along the orange axis or in and out. The actual electric field, right, can be anywhere rotated around the blue incident ray direction. But we can talk about its two components. So at a particular time, the electric field at a point can have a component along the orange axis or a component that's in and out of the screen. But when the light reflects at this special polarization angle, it will only have a component that is in and out of the screen in this picture. Now, the reason for this, you can argue, is the light that reflects is actually coming from the atoms in the second material. The electrons are being driven in that material by the incoming electric field of the incident wave. The electrons move, and when they move, they give off light. That, in fact, produces the transmitted light and the reflected light. But if you look at this ray right here, this transmitted ray could have two possible electric field components along the orange arrow direction and again in and out of the screen. Notice that both those directions are perpendicular to the blue transmitted ray direction. So the electrons in the second material, those atoms are being driven by electric fields that have these two possible components down here. But if this angle right here between the reflected ray and the incident ray is 90 degrees, this orange direction down here is parallel to the reflected ray direction. Right? But light can't have the electric field parallel to the direction of propagation. So there's no way that these oscillations down here that would be along this orange direction, these electric field oscillations, they can't produce light that travels in a parallel direction. So it's only the electric field down here with a component that is in and out that can produce the reflected light right here with an in and out component. And it's only when this is 90 degrees right here, that angle. That's known as the polarization angle. Okay, so you should know that light can be linearly polarized when it reflects. Now you should be able to describe the polarization direction, and that is going to be what I call parallel to the surface. The interface right here, this horizontal interface, can you imagine the actual surface plane? It's like if you held up a piece of paper, right, that is parallel to your desktop and place its edge right on the line of that interface. The actual surface of that paper is parallel to your desktop. Now I'm assuming that your monitor is on a desk with a horizontal surface, that you're not laying in your bed right now, right, with your phone held up to the ceiling, okay? So the surface would be horizontal in this case, in the picture. Notice that the electric field axis in and out of the screen of the reflected light is parallel to the reflecting surface, okay? All right, now, another thing to note is as the angle of incidence gets closer to this polarization angle, more of the light that's reflected is linearly polarized. So it's a gradual thing. At that special polarization angle, all of the light that's reflected will be linearly polarized. Okay, now the polarization angle you can actually calculate for a given interface. It turns out that the tangent of the polarization angle is n2 over n1. Okay, n2 over n1. And we can actually derive that. You want to derive that? Let's derive it. Okay, it's not hard to derive. So right here, we just have to use Snell's law. Here's my interface. Here's my surface normal. This light's coming in like, oh, I got to be careful how I draw this. So I'll do that. I got to go perpendicular like that. Okay, so this is N2. This is N1. Now the light's got to come in like this, because this is theta polarization, which is equal to this angle by the law of reflection. This, by definition, is going to be 90 degrees, and this is theta 2. Okay? All right, so then what you say is, okay, I'm going to use Snell's law. N1 sine of theta 1, which is the polarization angle, is N2 sine of theta 2. But wait a second. I can write theta 2 as, if you look at that picture, right, that's got to be 90 degrees minus theta p. Why? Because I have to get theta p, right, this theta p right here, plus my 90 degree angle, plus theta 2 has got to be 180 degrees. Okay? Well, then the sine of 90 minus theta I can write as the cosine of theta, right? So now I have n1 sine theta p is n2 cosine theta p. Guess what? I can find the polarization angle for a particular interface by doing an arctangent, right? So the tangent of theta p is going to be n2 over n1. Okay? So that's where you get that formula. Okay, let's go back here. Oops, I went to the wrong place. All right. Okay, guys. Now, let me see. These just gives you some typical values. So you can see right here that if you're talking about light reflecting air off water, the polarization angle is about 53 degrees. And as I was saying, so if a light ray comes in at 20 degrees, a little bit of the light that's reflected will be linearly polarized parallel to the water surface, okay? If a ray's coming in at 50 degrees, much more of that light that's reflected is going to be linearly polarized. And at 53 degrees, right, theoretically all the light that's reflected will be linearly polarized parallel to the water. And for an index ratio of 1 and 1.5, it's about 56 degrees, okay? All right. I do want to mention that if you have polarized sunglasses, so if you buy a pair of sunglasses that supposedly are polarized, what they do is you have these polarizing filters, these dichroic polarizers on the lenses, and they put the transmission axis or polarization axis vertical. Because what the polarizing sunglasses are supposed to do is to reduce glare. Glare is basically reflected sunlight. Now, most of the surfaces that are reflecting sunlight are horizontal. Think if you're out on the water or you're skiing, right? Lots of horizontal surfaces that are reflecting sunlight towards your eyes. A lot of that reflected light is going to be linearly polarized parallel to the surfaces, which are horizontal. So a lot of the reflected light will be linearly polarized with the horizontal electric field oscillation axis. So you have these polarizers with their transmission axes vertical, and a lot of that energy is going to be absorbed. That's how they reduce glare. Okay, you know what? I'm going to stop right here. I'm going to make 2 videos. You are responsible for the stuff to this point. Okay, so I'm going to go ahead and end this show. And let me just show you in your summary notes. You can see right here, this is the section on polarization. It talks about the law of Malus. It talks about how a linear polarizer works, the law of Malus, you should know. And then linear polarization by reflection, which an older name for this is Brewster's law, because again, the polarization angle sometimes is called the Brewster angle. Okay, so, and that's it. All right, and then I'm going to end the video. I'll make one more video where we talk a little bit more about polarization and then scattering and absorption. But that again is, quote, bonus material. Okay, bye-bye.